Wait, how are we supposed to finish the class? Have we even started yet?
Let's not talk about it. By the way, have you seen Mr. Alex' new haircut? Doesn't he look great? Doesn't he look great all the time?
And that's why touching the copper wire when the circuit is above 5 amps will be fatal. So it is recommended that no one touches it when the circuit is plugged in.
Wait, what did Jesus say?
I think he recommended us to touch it. I mean, like, it looks like a Van de Graaff generator, right? Otherwise, why would he recommend us to touch it?
He said it's supposed to be no shit.
Whatever, man, let's just touch it.
No!
Where's teacher?
It's everyone.
Hey, so apparently I was sent by the God to teach you idiots about the danger of electricity. You are the idiots, right?
Yeah. You look familiar. You're the guy from Tango. Don't Tango.
Yeah, aren't you Heinrich Lenz from NASCAR?
Wait, what? Don't even compare me with that idiot. Come on, I'll bring you to Sealand so that you know how dumb he actually is.
Tall and tan and young and lovely, the girl from Ipanema goes walking, and when she passes each one, she passes close. When she walks, she's like a samba that swings so cool and sways so gently that when she passes each one, she passes.
Alright, fine. Out of both laws, which do you think is better?
Don't ask us, we don't even know which laws which. So my law states that induced magnetic field opposes the change of the initial magnetic field that created it. And secondly, the induced force will oppose the direction of motion of the conductor.
Next, my law which is better states that changing magnetic flux through a loop of wire will induce an EMF.
Hold on. I said we are on the whiteboard. Anything to do with the laws you guys just explained.
Finally, we are back to the graph again, and this time around the orange color circle will indicate your coil and the green color line should indicate your magnetic field line. Okay, so the coil is actually turning in a clockwise manner and it turns back to its original position right here. These two graphs are actually flux versus time graph and EMF versus time graph. I'll begin with this first and then I'll further explain the EMF versus time graph. Okay, so you already know that flux is actually B multiplied by A, where B is your magnetic field strength and A is actually your area of coil. So when it's at this position, it is actually parallel to the magnetic field line. So your flux is actually 0. When it slowly turns to this position, which is perpendicular to the magnetic field line, you can actually get your maximum flux right here because there's a maximum area of the coil. When it turns back down to its parallel position, it gives you a 0 flux again, and then when it turns to this position, it's actually upside down of this one, the second one. This will actually give you a negative maximum flux, and then when it turns back to its original position, this will eventually give you a 0. So you can know that this is actually looking like a sine graph. The next thing is, I'll explain about the EMF versus time graph. The interesting point here is actually I can deduce my EMF graph by using my flux versus time graph. As you already know that EMF is actually the rate of change of flux, so the value of it should actually be the gradient of your flux graph at each point. So let me take this point as an example. When it's at this position, which is maximum flux, this is actually giving you a 0 gradient. So for EMF, you should get a zero EMF right here, and when position also, zero gradient, zero value for EMF. And when it's at this position, this is actually a maximum gradient that you can get from this sine graph, and you will get your maximum EMF right here. Same goes for this point and this point. You will get your negative maximum and your positive maximum. So EMF graph is actually looking like a cos graph. To conclude, when you have this position in your coil, you will actually get zero flux and the maximum EMF induced. When it's in a perpendicular position, slowly turning to this perpendicular position, the flux is actually maximum at here, but then the EMF induced in the coil is actually zero. So when it turns again, it goes down to its maximum EMF induced, then goes back to zero EMF induced, and to your maximum EMF induced. Your coil keeps turning and turning, and you will induce an EMF in both directions, so you will get an alternative current.
What I have here is a working model of how an electric motor works. The red arrows here determines the direction of the current. Over here, it's going into the screen, and over on this side, it's going out of the screen. Now, you're able to determine the direction of force by knowing the direction of the magnetic fields, which are going from the left to the right. The force over on this end will be going downwards, and the force on this end will be going upwards. Now, with these two forces acting at the same time, the coil will turn in an anti-clockwise direction, and this anti-clockwise direction will cause a change in magnetic flux. And according to Faraday's law, the change in magnetic flux over time will induce an EMF. And this change in magnetic flux can be calculated by using the equation of V, which is your magnitude of your magnetic field, and A, which is the area of your coil, which is over here. And now, this induced EMF will then oppose the direction of the initial current, which will be going out of the screen on this end and into the screen on this end. And now, this back EMF, which is actually your induced EMF, will cause a reduction in voltage. And now, to actually put it in an equation, let's say your input over on this end is 5 volts, and your back EMF is negative 2 volts. And your equation will be like this: 5 volts minus 2 volts. You will get a net output of voltage as 3 volts. Thus, it can be concluded that your input voltage is a little way more than your actual voltage. And as your coil spins faster, the change in magnetic flux per time increases, causing your EMF to increase.
Okay, before learning what the graphs are, you actually need to know what an AC generator is. An AC generator basically looks like this, and this is a bar magnet. This is a coil. If you turn it right, you can actually produce electricity through it. And these two components are called slip rings and carbon brush. So this component will connect the coil to an external circuit. In this case, we are using a voltmeter so that we can know if there's actually electricity flowing through it. Okay, if I start the animation, it actually gives me a reading. So why does this happen? Why does the turning of the coil actually gives you electricity? It can be explained based on Faraday's law, when the coil is actually cutting through the magnetic field line and it undergoes a change in magnetic flux. So a change in magnetic flux will give you an induced current through it, and this induced current will flow through the coil to the external circuit, and will gives you this voltage reading. Bear in mind that the voltage reading actually goes from the positive to negative back and forth. This is because it's actually an alternative current, which is because we are using two slip rings, not just one commutator. So the next question is, how do we know the direction of the induced current? Red arrows indicates the direction of the current, the black arrow indicates the direction of the motion. So if I pause the animation here, okay, according to Lenz's law, right, the induced current will then give you a magnetic field line that will interfere with a permanent magnetic field line, should gives you a force which should be opposing the force causing it. So in this case, the current should be going here, which will gives you a force going inwards because it's interacting with the external magnetic field line, and the force going inwards is actually counteracting the force going outwards, which is causing it. Or in another way, if you want to learn it easier, you can actually deduce the direction of the current by using Fleming's right hand rule. So the diagram here shows clearly that your thumb will be the direction of the motion, and the magnetic field will be indicated by your index finger, and your middle finger will be the direction of your induced current. This discussion is useless. There's no point revolutionizing this concept and there's nobody to present it.
True, but at least we are famous for what we are.
Wait, we still can resurrect these students to help us publish our new discoveries, right?
Yeah.
Arjun, Ihan, Arjun, are you okay? Why did you touch the power supply without my permission? Why?
You don't know the concept, right?
Two, one, action.
So exactly how are we supposed to finish the investigation class?
I don't know.
Wait, it was started yet?
Try. Should be okay.
Yeah, you look familiar. Are you have for textbook?
Aren't you language slash finance law?
I have to say, you look better in textbook.
Yeah, man, you look that ugly now.
Out of both... Shit, okay, sorry. Alright, fine. Out of both laws, who do you think which is better? Shit!
Now you know how we feel.
Why are you so handsome, Eugene?
Hey!
Eugene, why are you so handsome, bro? Yeah, shit. So you're gonna look at the phone the whole time, not the camera.
Yeah, then you say, wait,
Oi, champion!
resurrect
Shut up!
these students.
So, wait.
But, or you want to just keep jumping until you both are like at the same
Okay.
frame? Huh?
You jump.
You jump so low, walao.
I think it's okay.
doesn't matter how high you jump. As long
Yeah,
as
yeah.
you land at the
What you thought you can get overpriced by this?